All right, everybody, we're going to do a video here on linear regression. Because I teach stats at multiple schools, I'm going to do this video on linear regression for both my Ferrum students as well as for my Dominican students. Dominican students, the stuff that I'm referencing, I can certainly provide to you, but that's not an assignment. It's only for reference. To my folks over at Ferrum, this is an assignment, and you can find it in Brightspace. So I'm going to walk you through it and then give you the opportunity to do one of the problems on your own based on linear regression. So again, there is an assignment for the Ferrum students, and there is not an assignment for our my folks over at Dominican, because we've already done some assignments. This is just to enhance your knowledge. So here we go. All right, here we go, everybody. Okay, so let's start talking about linear regression. So, and I have some cues here. If it says whiteboard reference, that just means I'm going to draw something and break it down for you guys. So let's go up to the top here. All right, first of all, linear regression, also called regression, is a statistical procedure used to determine the equation of a regression line to a set of data points and to determine the extent of which the regression equation can be used to predict values of one factor given known values of a second factor in a population. The predictor variable or known variable X is the variable with the values that are known and can be used to predict values of another variable. The criterion variable, or to be predicted variable Y, is the variable with unknown values that can be predicted or estimated given known values of a predictor variable. FYI, linear regression, and this is just reiteration here, linear regression is used to predict the values of Y, the criterion variable, given the values of X, the predictor variable. Example 1. Now this might be interesting. You might actually use this in the real world. If we look at this right here, a job candidate wants to know how quickly a business tends to promote its employees. He takes a sample of 6 employees and records the number of years they've been employed and the number of promotions that they have received. This is the information below: years of employment versus number of promotions statistically. In this example, the job candidate is interested in predicting the number of promotions given the number of years an employee has been employed. Thus, years of employment is the predictor variable X, and the number of promotions is the criterion variable Y. To find the equation of the regression line, we use the method of least squares, which was first introduced about 2 centuries ago by French mathematician Adrien Legendre. But first, we have to ask 3 questions to better understand linear regression. And this is just conceptual, okay? So first question, is the linear pattern evident in the set of data points? Is it? And how do we know? We observe a graph or a set of data points to see what pattern emerges, potentially maybe like a scatter plot. Secondly, which equation of a straight line can best describe this pattern? Well, that's your method of the least squares, which I'll walk you through a little bit later on in this lecture. The next thing we're going to look at is, are the predictions made from this equation significant? And if so, we want to use our analysis of regression to answer that question. So let's take another look at the first example, but with a smaller data set. Let's say the predictor variable is the number of years worked, X right here. And the criterion variable Y is the number of promotions that someone has received. And it's probably be a capital Y. Suppose we measure 2 factors. One predictor variable plotted on the X-axis and one criterion variable plotted on the Y-axis. So if we go ahead and we look at that, I'll whiteboard this in just a second here for you guys. The table above lists data points, okay? The distance of these data points from the regression line is 0. However, data points B and C, right here, data points B and C, let's say these right here would probably be the best way to explain it, fall below the regression line -2 units. And the data points on the regression line is 0 plus 0 squared plus, yeah, 0 plus 0 plus 2 minus 2 minus 0. We're not squaring them yet. A zero solution will always occur when we sum the distances of data points from a regression line, same as the outcome observed when we have sum the deviations of the scores of the mean. So what does that mean? Let's take a look at the whiteboard here. So what we're talking about is we have this right here, which is our y-axis, and we have this right here, which is our x-axis. On this side, we're going to put our criterion variable. Then, and that's of course going to be y, okay? Then we're going to have our predictor variable, which is x. So x is going to predict y. Predictor variable. Bear with me, I'm writing with the mouse. Variable. And that is going to be our x, okay? So we have over here, we have 1 unit, we have 2, and this goes all the way to up to 10. So we'll go ahead and just number those 3. You can feel free to draw along with me if it'll help you sort of understand this conceptually. 5. Now, this is just for the sake of the concept. You don't have to have exactly the right same amount between everyone. I mean, in an ideal world, you would, but you don't have to, just for the sake of understanding here today. 9, and then we'll say 10's up here. And then kind of the same thing. That's 1, and that's 2, and that's 3, and that's 4, and that is 5. All right, so let's go back to our Word document, everybody. So we were talking about this. Suppose we measure 2 factors, one predictor variable plotted on the x-axis and one criterion variable plotted on the y-axis. The table above lists the data points, and we have our scatter plot, and then we look at where these points fall from the regression line. So what that really means is we want to look at this first image here that I drew on the whiteboard, which is this one right here, our criterion variable and our predictor variable. So X is predicting what's happening here. So B right here is our next variable, which is the number of, sessions. And in this case, it's 2. It's 2, and it falls 3 units from the criterion variable. And then we have another one right here, which is 8 in our data, and that falls, actually, should we have 3? So 3 right here, where they intersect, and 2, which are literally 2 units away. And then the same thing here, when we have 8, it falls 2 units. So that's the smallest amount of the sum of the squares has to do with where the lines on the where the data is against the regression line. That's where we come up with that for some of our squares, for the lowest possible sum of the squares. Any other line in the regression line. All right, so the next thing we want to talk about is any other line in the regression line will produce a sum of the squares larger than 8 units in this example. To illustrate, if we fit another straight line to the same data, and I'll show you this on the whiteboard, the distance of each data point from this line is plus 3 units. All right, let's talk about that. So what we're talking about is any other than the regression line will produce a value of the sum of the squares that is larger than 8 in this example. To illustrate, we fit together the straight line to the same data, which I will show you on the whiteboard, and you'll see the distance from each data point is plus 3 units, plus 4 above the line, negative 2 units, negative 3 units below the line. If we compute the sum of the squares for these distances, we obtain sum of the squares equal to 3 squared plus 4 squared plus or minus 2 squared plus or minus 3 squared is equal to 37. The result is much larger than the sum of the squares being 8, which is the value we obtained for the least squares regression line. Different lines of different values of the sum of the squares. Regression line, or line of best fit, is the line with the smallest or least value of the sum of the squares. So let's look at that on the whiteboard. What I just mentioned is this right here. Okay, let me make that big for everybody so you can see it. So this is what I was talking about. If we draw this straight line to summarize and we look at more of the values, these start to get be much bigger, and then the sum of the squares is going to be equal to 37. The sum of the squares, because 3 units, 2 units, 3 units, 4 units, that's literally where that came from. I'll pull it up again if you just want to pause for a second. You want to hit pause or see that. So if you look at the paragraph I just talked about in the Word document and look at this right here, that's exactly what I'm referencing. All right, moving on. Let's go back to our desktop here. So the slope and y-intercept of a straight line. If we know the equation of the regression line, we can predict values of the criterion variable y, so long as we know the values of the predictor variable x. To make use of this equation, we need to know the equation of a straight line. The equation of a straight line is y is equal to bx plus a. And a lot of times we probably would write this bx, and this would probably be italicized to show that it's a slope. But really just remember those letters, okay? So in this equation, y is the value we plot for the criterion variable, x is the value we plot for the predictor variable, b is the slope of the straight line, and a is the y-intercept, where the line crosses the y-axis. To make use of this equation, we need to know the values of a and b in this equation. In this section, we explain what a and b measures are. And in the upcoming section, we will use the method of the least squares to find the values of both a and b. The slope, represented as b, is a measure of how much the slope represented as b, let's try that again. The slope represented as b is a measure of how much a regression line rises or declines along the y-axis as values on the x-axis increase. The slope indicates the direction of a relationship between two factors, x and y. When values of y increase as values of x increase, the slope is positive. The regression line will appear as if going uphill, illustrated with a hiker on a regression line. So whiteboard example to illustrate, that is this right here. Talking about this right here, this image, okay? This is the hiker going up the hill. This is a positive factor x and factor y. So going back to where we were, excuse me. So when the values of y decrease as the values of x increase, the slope is negative. The regression line will appear as if going downhill, illustrated with a skier on the regression line in the upcoming whiteboard drawing. And that whiteboard drawing for our negative slope looks kind of like this one right here. Let's make that big for everybody. This one, here's your skier on the negative slope. Thus, if we go back to our desktop here, thus the slope of a straight line is used to measure the change in y relative to the change in x. So the slope of b is equal to the change in y divided by the change in x. The y-intercept is represented as a, where the straight line crosses the y-axis on a graph. More specifically, the y-intercept is the value of y when x is equal to 0. The y-intercept is the value of the criterion variable y when the predictor variable x is absent or equal to 0. So using the method of least squares to find the best fit, we use the method of least squares to find the equation of the regression line, which is the best fitting straight line to a set of data points. Using this method, we will measure the sum of the squares for factor x and factor y, and then use these values to compute the slope b and the y-intercept of the regression line. To use the method of least squares, we complete 3 steps: compute the preliminary calculations, calculate the slope, and calculate the y-intercept. Factors, so another example here. That's probably, I think this is example 2. Put that here, example 2. So factors that can predict the effectiveness of behavioral therapies are of interest to clinicians and researchers. As an example of research for this study, this area of study, suppose a psychologist wants to predict the effectiveness of a behavioral therapy measured as the number of symptoms that patients express, to give the number of sessions a patient attends, given the number of sessions a patient attends. She selects a sample of 8 patients who express the same number of symptoms at the start of the treatment. She then records the number of sessions attended, X, and the number of symptoms expressed, Y, by each patient. The attached table or Excel document show what she has recorded. So let's look at that together. So here is our Excel. Just a second to bring that up, everybody. And we'll. Now with this file here, you can just scroll down, okay? So predictor variable, criterion variable, we talked about that just now. Number of sessions, number of symptoms. Again, X, this should really be X, and this should really be Y. I'm gonna put those in the center here, like that, okay? So that's what I'm talking about, number of sessions versus number of symptoms. All right, so let's go back to our Word document here. Actually, we just share the same desktop, and we'll go back to Word. All right, so that's it. I just talked about this right here, okay? So step 1, compute, not computer. Oh, I did that. Compute the preliminary calculations. We begin by making preliminary calculations, which are shown and or in the accompanying Excel file, which is the Excel file. The signs plus and minus of the values we measure for each factor are essential to making accurate computations. The goal of this step is to compute the sum of the squares needed to calculate the slope and the y-intercept. We will describe each calculation in the table from left to right. Compute the average X and Y score. In this example, the number of sessions attended is the predictor variable X, and the number of symptoms expressed is the criterion variable Y. In the table, each column of values for X and Y was summed and then averaged. So the mean of the X values are 5.25 and the mean of the Y values are 2.75. So let's just look at what that is here on Excel so that you can see it. And this is right here. So all I did is I just did the mean. Now this is your formula for the mean, okay? You take the average is equal than your range, okay? And this is that mean right there. That's all we're talking about at this point in our Word document, okay? So the next thing we're looking at is subtract each score from its respective mean. In the third column, each score X is subtracted from the mean X, and in the fourth column, each score is subtracted from the mean Y. Remember, the sum of each of the column, the sum of scores from their mean is equal to 0. So what we're talking about is this right here. So make this, zoom in a little bit for everybody. So what we're talking about is this X was minus this mean right here. So I'm taking 9 minus this, 5 minus this, etc. for this column. This one is Y right here minus the mean number of sessions, 2.75, to get these values. Then this right here, we're multiplying these two to get these numbers. And then this, of course, is X minus the mean of the scores, which is right here, okay? Minus that, and then we square it, okay? So we take X minus the mean of X and then square it, and we get these numbers right here. And then, of course, this column, after we do this calculation, is known as the sum of the squares, X, Y, and this is the sum of the squares, X. So again, this is, we multiply these two to get this, and we take X minus this mean over here to get that column. That's where those came from. And you can see which columns in the formula here that I've done, just to help make that clearer for you if you need that clarity to further understand what we're doing here. So then the next thing we do is the sum of the scores for the XY, also called the sum of the products, is negative 22.50. So where is that in our Excel? So the sum of the scores, I don't think we have that. I believe that is right here. No, that's not right there. Okay. The sum of, make sure I can, no, multiply across the rows and through these, sum of these scores is the sum of the squares for XY. So sum of the squares XY. So let's make sure that we're looking at the right thing here. Sum of the squares. Oh, the sum of the squares, the sum of the products for X and Y. So I believe we're going to go like this. Let's insert. Let's see if we square all of these. What does that do? That would be H 27 to the second power. No, it doesn't work. That's circular. G 27 to the second power. And then if we square these, I don't think that's what it's wanting us to do, though. No, we're not doing that. We're just going to scrap that. So the sum of the products of both X and Y multiply and sum the deviation scores. So we did that. Multiply and sum the deviation scores. And we compute the triple mean, multiply the crossovers in the third and fourth columns. Some of these squares is also, oh, okay. So that should actually be equals. Just stop the share just so I can make Excel make a little more sense for everybody. Stop here and we'll just pause. All right, everybody, I figured that out. Be careful with your Excel. You want to make sure that you have all your calculations correct here. So what we're talking about is we took all of these. Okay, so we figured out what our means were. Then we subtracted our means, and then we subtracted the y, the x minus the mean of x, and the y minus the mean of y, and we multiply these together, and then we got these numbers. So this times this is that. If you sum all of those, you get negative 22.5, sum of the squares x, y, and if you sum the squares all of these, you get 39.5. What was 39.50? What was happening is there was a formula or two that was off in Excel. I've since saved this, and of course, for those of you that are doing the worksheet over at Ferrum, I'll update that, and folks at Dominican, don't worry about that. Now that file actually makes sense. That was just a formula that was off. So let's go back to where we were. So that's how we got this. Multiply and sum the deviation scores of x and y. We computed deviation scores by subtracting each score from its mean. Then multiply across the rows in the third and fourth columns. The sum of these scores is the sum of the squares for x, y, also called the sum of the products, which is negative 22.5. And then multiply and sum the deviation scores for x, multiply the deviation score of x value by itself. The sum of these scores is the sum of the squares for x. Sum of the squares x is equal to 39.5. Step 2, calculate the slope. The slope of a straight line indicates the change in y relative to the change in x. Because the value of SP can be negative or positive, this value indicates the direction that y changes and x increases. We will use the sum of the products, which is the same as SS, the sum of the squares xy, to estimate the changes in y, and we'll use some of the squares x to estimate the changes in x. Therefore, the formula for computing the slope b is equal to a change in y is equal to SSXY, or SP, sum of the products, divided by the change of in x, which is SS, sum of the squares x, or SSX, or however you want to look at that. Okay. So we already computed this. We know negative 22.5 for this, and 39.5 for the sum of the squares x, sum of the squares xy, sum of the squares x is negative 0.57. Next, we want to calculate the y-intercept, or a. The y-intercept is the value of y when x is equal to 0. To find this value, we need to know the mean of x, mx, and the slope we just computed. The formula for determining the y-intercept a is equal to my minus bmx. We already computed that my is equal to 2.75, mx is equal to 5.25, and b is equal to 0.57. The y-intercept of the regression line is is equal to 2.75 minus, so a is equal to 2.75 minus 0.57 times 5.25 is equal to 5.74. Because we computed the slope of b is equal to -5.7, the y-intercept of 5, the y-intercept is a is equal to 5.74, we can now state the equation of the least squares regression line as y is equal to -0.57 x plus 5.74. In this equation, y stated that, or y hat is how you can refer to it also, is the predicted value of y given values of x. For example, suppose we wanted to make a prediction. If one patient has attended 4 therapy sessions, x equals 4, we can substitute 4 into the equation and solve for y. Y is equal to -0.57 times 4 plus 5.74. Therefore, y is equal to 3.46. In this example, we expect or predict that a patient will express 3.46 between 3 and 4 symptoms following 4 therapy sessions. In this way, we use the equation to show how many symptoms we expect a patient to exhibit after a particular number of sessions. Now, for my Ferrum folks, go ahead and you can do this right here using the same steps I just walked you through, which is this data. So take this data, make it into a table like this, and follow the steps. And for my Dominican folks, again, just examples. If you want these worksheets for practice, just send me an email. Hope you learned something about linear regression. Take care, and I will see you in the next video, and I'll break down some more stuff.